All my videos in this series will be of organic chemistry. For physical and inorganic chemistry, I will make another playlist. It will be focusing your basic chemistry honors syllabus. It will be beneficial for other students also for the detailed and advanced learning. In this video, we will learn atomic orbital in the context of organic chemistry. It is a region in space where an electron is likely to be found. There are different kinds of orbitals which have different sizes and different shapes. Different types of orbitals are s orbital, p orbital, d orbital and f orbital. But we all know that organic compounds are mainly made of carbon and hydrogen. Besides this, oxygen, sulfur, halogens, nitrogen, phosphorus, etc. may also be present. Since the main constituent is carbon, the atomic orbital s and p are mainly involved in the formation of organic compounds. So let's have a look on s orbital. This orbital is symmetrical in shape. The center of the sphere is at the nucleus of the atom. As the orbital is spherically symmetrical, its charge density is symmetrically oriented about the nucleus, and it is a non-directional orbital. Being close to the nucleus, electrons of this orbital are very strongly bound to the nucleus. As there is no charge density at the center where the nucleus lives, this is called nodal point. But remember, there is no nodal plane. Electrons being strongly bound by the nucleus, s orbital is very strong and it is most stable, having less energy. Let's move on to your p orbital. The p orbital is dumbbell-like. There are three types of p orbital, viz. px orbital, py orbital and pz orbital. These three orbitals are degenerate, that is, they are of equal energy and they are identical in shape and sizes. But the difference in their spatial orientation, that is, these three orbitals are oriented mutually perpendicular along x, y, and z axis. So, p orbitals have directions. Here you can see the dumbbell-like charge cloud of px orbital lie along x-axis. Here of py, it is along y-axis, and of z, it is along z-axis. The probability of finding an electron at the nucleus of p orbitals is 0. So this is called nodal point. The plane containing nodal point and bisecting the two lobes of p orbital is called nodal plane. This is the nodal plane of px orbital, this is the nodal plane of py orbital, and this is the nodal plane of z orbital. Now, your hybridization. Atomic orbitals, whether vacant, half-filled or filled in excited state, mix up to form new orbitals having different charge densities form the pure atomic orbitals. And the process by which this orbital mixes up or form is called hybridization, and the new orbitals are called hybrid orbitals. They have same shape, energy and size, that is, they are equivalent, but they differ in their spatial orientation about the nucleus of the atom. Generally, in organic compounds, three types of hybridizations is possible, that is sp3 hybridization, sp2 hybridization and sp hybridization. We will discuss them one by one. First come your sp3 hybridization. When one s orbital and three p orbitals mix up to form four identical hybrid orbitals, sp3 hybridization occurs. Let us consider carbon atom having atomic number 6. In ground state, it have electronic configuration like this: 1s2, 2s2, 2p2. But in excited state, this one electron of 2s orbital move to 2p orbital and create 4 half-filled orbital. This 4 half-filled orbital of 1s orbital and 3p orbital mixes up to form 4 identical sp3 hybridized atomic orbitals. These four identical sp3 hybridized atomic orbitals take the shape of a tetrahedral of 3 bond angle 109 degree 28 minute. At the center of the tetrahedron, the sp3 hybridized atom is placed. Generally, for carbon atom, sp3 hybridization is observed when the tetravalence of carbon atom is being satisfied with four atoms by forming four single bonds with them. In methane, the four atoms are four hydrogen atoms of 1s orbital. Similarly, in methylamine, the four atoms are three hydrogen atom and one nitrogen atom. This is the 3D expression of an sp3 hybridized atom, and this is how a tetrahedra looks like. In sp2 hybridization, one s orbital and two p orbital mix up to form three hybrid orbitals of identical shape and size, and they are called sp2 hybridized orbitals. But here the pz orbital remain unhybridized. An sp2 hybridized carbon atom has trigonal planar shape. All three sp2 orbitals remain in the same plane. Pz orbital remain perpendicular to that plane. This is the image where you can see that the CCC bond angle of sp2 hybridized carbon atom is 120 degree. At the center of trigonal planar, the sp2 hybridized atom is placed. For carbon atom, sp2 hybridization is observed when tetravalence of carbon atom is being satisfied by two single bonds and one double bond. So, all double bonded carbon atoms are sp2 hybridized. For example, ethylene and benzene, where all carbon atoms are sp2 hybridized. sp hybridization occurs when one s orbital and one p orbital mix up to form two hybrid orbitals, and they are called sp hybrid orbitals. For carbon atom, being sp hybridized get linear shape. Here, two p orbital of py and pz remain perpendicular to each other. They do not participate in hybridization. Generally, triple bonded carbon atoms are sp3 hybridized. For example, acetylene and HCN or hydrogen cyanide. Here, both carbon and nitrogen atoms are sp hybridized. Now let me compare the relative energy content of sp orbitals and sp hybridized orbitals. The factor behind this is the more the s character of the hybrid orbital, the lower is the energy content and the higher is the stability. Previously, I have told you that the reason behind the more stability of s orbital, there I have said electrons being close to the nucleus of this orbital, they are very strongly bound to the nucleus. That is why s orbital is stable and have less energy compared to other orbital and hybrid orbitals. As the energy increases with decrease in s character, the relative stability decrease with increasing energy. Here you can see in the table that the percent of s character decreases from s to p orbital, and the relative stability also decreases going down the group. So you have to remember the name of the orbitals and hybrid orbitals, their percentage of s character, their orbital length, their shape, and their presence in single, double, and triple bonded system. So if you have any doubt, you can ask them in the comment section.